Welcome, ladies and gentlemen, for this special series on exotic technologies on farming. We know that the whole world is hard pressed for environmental concern, carbon footprint, and blah, blah, blah. And the imperative is very clear. It's writing on the wall that anything which is moving better be lightweighted, whether it is aircraft, whether it is train, whether it is ship, whether it is because anything which is consuming energy, momentum, which has kinetic energy, if it is lighter in weight, it saves. There is another aspect to it. Of course, there are two aspects of saving. One is saving during its lifetime, that is the running cost. And other is, of course, the initial carbon footprint about how much material we put into the product. So that aspect also comes in lightweighting. If you put lesser material, that much lesser carbon footprint goes into it. So from both the points of view, it will be environment friendly to use some of these exotic technologies going further to make anything that moves lightweighted. With this in mind, all these exotic technologies have developed all over the world, mainly for aerospace, automotive, railways, and shipping, and various sectors. And the technologies are today what we are talking is primarily about rotary swaging and axial forming. But of course, there are many other technologies which go into it, like use of composites, like hot forming, hydro forming, flow forming. So we'll be talking about all these technologies one by one. We'll be roping in the experts from all over the world, like we have one, Mr. Peter Karch today, to talk about rotary swaging and axial forming. So with this, we get started. Mr. Peter, hi. Would you kindly introduce yourself?
Yeah, thank you for this opportunity to speak about these wonderful and really interesting technologies. My name's Peter Karch. I'm a classical mechanical engineer, studied here in Germany, worked in Germany since then, and I had some years in the automotive industry, in parts producing, manufacturing, before I came to FELSS. This is something like 12 years ago already. I started here learning about axial forming, rotary swaging, worked then in manufacturing, so produced parts myself, had my own projects, and now I'm here, one of the technical people at FELSS and also selling these machines and also the technology, of course.
So FELSS is a pioneer in this technology. Mr. Peter, would you kindly talk a little bit about FELSS as a company, what they are doing? And
Yeah, you can say so. They are really pioneers. Actually, they started beginning of the last century. I think it was 1945, something like that. They started with a small manufacturing, and then they went on and on. First, they did this rotary swaging technology. Rotary swaging is something like if you think about a sledgehammer, two hammers working against each other, then you have material in the middle and you start forming this material. From this very basic idea, we started the beginning of the last century here with in-feed swaging. Then they developed the recess swaging technology, added some CNC programming on that. And today we have machines which do a rotary swaging procedure completely CNC controlled. So you can move the material from one portion of the part to the other portion wherever you want that. So this was forming in radial direction. Parallel to that, they started a development in axial forming, which means now coaxial to the shaft or to the workpiece, and this was called axial forming. Actually, it came from a pressing idea, and we knew that each time when you press down a forming die over material, you need some oil in the gap in between. If you do not have that oil, your rejecting forces will increase tremendously. It's simply a friction problem here. And now they started to use oil in between this gap, but they saw that after 1/10, 2/10 of a millimeter movement, the oil film broke. So they lifted the tool again, the oil came back, and then they restarted working. And from this basic idea, recursive axial forming was developed. And these are the two technologies we use at the moment. So in radial direction, it is rotary swaging. In axial direction is axial forming.
Something like reverse wood packing. Yeah. I have a small request for the audience. Please feel free to put any questions in your comment so that we can get answers from Mr. Peter. Like the video, please give comment, please give your opinion. If you have any questions, please feel free to ask. We have this forum open. Mr. Peter will be so kind to always entertain any questions even later. This is a small request. Mr. Peter, what was the historical perspective of these technologies? Like, why did FELSS develop these technologies? What were the main drivers for developing these technologies?
Lightweight design, and in all cases also cost. It's a little bit an issue. So first, let's go to rotary swaging.
Yes.
Rotary swaging originally came from, or here in Germany has been developed from gold industry. In gold industry, you try not to waste material. And therefore they used this technology to form gold and to form precious materials, let's say like that. This came later on to glasses, what you wear.
Yeah.
In your glasses, Avinash, sir, you have two wires.
Yes.
They are definitely rotary swaged because they have a different diameter and very easily made by rotary swaging and very fast. What we have seen is that rotary swaging was really fast. And this was the reason that more and more companies got attracted to the idea itself. Then we started with, in the automotive industry, first with steering systems. So these steering columns which go from your wheel down to the gear drive of the steering. They have been quite a success because at that time they were turned or they were solid. Now all of them, all over the world, they are more or less all of them. They are hollow and they are swaged. Axial forming had a little bit a different start. Axial forming, well, the idea of pressing, this was well known.
Yeah.
But with the idea of recursive pressing, so just what I explained later, you lift it, press again. You lift it, you press again. So that you have always your oil in the gap means that you can produce much smaller wall thicknesses, or you can form much smaller wall thicknesses. I think the smallest what we form today is something like 3 millimeters or 2 millimeters under the spline. It's very hard to produce this with another way. And this was when we had our breakthrough with this technology, also in automotive.
Now that you said something about there is no alternative technology which can do the same thing, can you give some more example where only rotary swaging and axial forming is required? You gave one example just now. That
now let me think about this. Well, let's start with rotary swaging first.
Yeah.
I think it's the speed.
Okay.
You have other forming technologies which also work on which also work cold. Which cold means for us, we do not heat up the material. Cold means up to 100 degrees. The big advantage of rotary swaging is its tremendous speed. I just finished a project for a company which produces a new rotor shaft for e-cars. And they produce one rotor shaft completely in a time below 20 seconds. So each 20 seconds, you have one new shaft. And this is possible because the forming speed is really high. For axial
not all technologies are fast enough for mass production for automotive typically. So what you're saying is that rotary swaging happens to be one technology that is fast enough and it could give the cycle times that automotive industry would wish.
Right? Definitely. And very often we lead it. For example, for these special applications, we sometimes have two lathes or two additional machines which work in parallel just to feed the swaging machine. This is really a fast process. Same applies for axial forming, because axial forming, if you have something like a spline like this length, so like my 2 times my finger, 3 times my fingers. Usually you produce this in 15 seconds. So 4 pieces per minute. This is quite fast. You cannot make this with other technologies in this speed. So if you ask me what is our USP, I would say it's the speed.
So today the USP is speed.
It's the speed.
And of course, economy you have already talked
Excuse me?
about. economy. You are not wasting any material and
Yeah.
whatever we said some time back. So what do you think? What is the potential going further? How do you see the market developing for these technologies? Say, let us say 5 years and 10 years later. What would be your rough estimate or wish?
This is a rough estimate, because if I could give you a very precise estimate, I would be very rich,
Yes,
most
yes.
probably. I think in the next time or in the next years, we will see several trends. We will have small batches and we will have a variety of different shapes. I don't think that we will come back to the times when we had millions of similar parts,
Okay.
and these millions of similar parts went into a very, very large production lot. No, customers demand small batches, something like 20,000, 60,000 parts per year. And this means you have to change your machines quite often and quite fast. A typical changeover time for an axial forming machine is something like 20 minutes. This is only when I do it. So I'm not really experienced anymore. But 20 minutes is the usual time what you need to change over from one part to the other. For rotary swaging, it might be a little bit more, depending on the complexity of the part. But anyway, in half an hour, you are done.
Okay.
So this is a real advantage if you have a manufacturing with a high variation of parts. And this will be the future. This is what all our customers tell us. The second thing is on axial forming. What we see is the demand. It comes with the EV drive. This was from then, that you have connecting splines or connecting gearings which need to be more and more precise. As an example, we were coming from IT7 as a basic idea of the quality of the spline. Today, customers more and more ask for IT6, which is one class better, and one class in splining is quite good. So with recursive axial forming, you can do this. This is also one reason why we constantly improve the machines and work on that. A third thing which will come, and that's a very interesting thing for me as a technician, is helical gearing.
Okay.
Helical gearing, I just have, by chance, I have one of these parts here, such a rotor shaft.
Is it hollow?
If you replace this gearing, it's hollow, yeah. Otherwise, I could not lift it like this.
Yes.
By the way, very, very thin walled here.
What's the weight of this, by the way?
2.5, 3 kilo, something like that. Quite large.
Yeah, correct. Yeah.
What I wanted to say is more and more our customers ask for helical gearing in this area.
Yes, of course.
And the shorter these shafts here will get, the closer we are to the first contours of the shaft.
Yes.
And that means that you do not have the length
Yes.
to grind, for example. With axial forming, with your dies, you can go to something like 3 millimeters before you have to stop.
Yes.
You will never do this, for example, with a grinding device or with a mill, because you simply need the run out. This will be something very, very interesting for the future.
Now, I was going to ask you something actually, Peter, that, okay, in drive shaft, so far what I have seen is only splines, internal and external splines. But of course, bulk of the transmission industry is using helical gears. So it's an interesting idea to make hollow helical gears. Now, do you see that these technologies will come into that as well, to make big helical gears hollow?
I don't think you have another chance, because the shafts will be hollow.
Yes.
And the helical gear itself, do you mean the tooth will be hollow?
Of course.
Honestly, I doubt it. I think that the shaft itself will be hollow, but the tooth itself, that will be tricky, because think of the load and of the torque what you have to transfer with this.
Could be that it is able to transfer the load. That much section would be required in any case. Anything over and above can be reduced, can be made hollow.
Yeah, but let's see. Perhaps the development will be in this direction. I do not see it at the moment, but let's see.
Do you see the scope for these technologies increasing dramatically with EVs? Because in case of EVs, lightweighting is not just for, let us say, efficiency or carbon footprint. It is basically mileage per charge. How much your car will go with single charging. For EVs, definitely light weighting is a very important imperative. All the transmission for EVs are bound to be requiring these technologies sooner than later.
This is only one point, and I absolutely agree with you.
Yeah.
You will have an impact on that, and the impact will be that you are lighter.
Yes.
But there's also something else. The precision is better if you use axial forming, for example, than other means of forming, because the EV drives have a problem with sound, with
Okay.
noise. Formerly, the piston engine, they masked this.
All the other sound.
Yeah. If you hear something from your wheel, then it is mostly covered by the piston engine. If you hear something from your drivetrain,
Yes.
it's covered by the piston engine. The piston engine does not exist anymore.
Yeah.
So now you hear everything. And what we have seen is that the splines or the connection lines, what we have at the moment, must be much more precise than before, just to avoid noise.
Okay.
And this is a real business at the moment to increase the quality of the splines.
The customers will become more sensitive to even the small squealing noise or some other humming noises, which they were earlier not bothering that much, or they were not able to feel those things at all. Yeah, it's a good point, I guess. One doubt I have about these technologies that since it is forming, the volume of the part remains same before and after. And if we are moving the material axially, for example, does the end get spoiled? Do you have to cut off the portion of the end to get a normal surface? That you are scooping the material like this. So on the end, do you have some irregular feature that you have to get rid of?
First of all, yes, you have. Sometimes we are quite good in overcoming this issue. So these irregularities, what you call them, they are more or less in the range of several tenths of millimeters. So 0.1, something like that, or 0.2 if we are talking about small wall thicknesses. What we have seen on steering shafts is customers do not take this off.
Okay.
Because the only possibility what you could do is you make it a little bit longer, and then you simply cut it off.
You simply cut off.
And then you have a similar length to all of them. And at the beginning, we really did it like that until customers came to us and told us, it's not even necessary. This is not a technical point. So this has no function. So whether it looks like a wave a little bit or whether it's completely round, we do not care. So this is the first case. The second case is when you have really big wall thicknesses. So if we are talking about 10 millimeter wall thickness, for example, then you will see an effect that the material distorts very strongly.
Okay.
So in here you have something like 1-2 millimeters of not of forming, but of deformation, real deformation. And we cut this off. But it's absolutely right. So
if it is small, maybe you can do deburring or something like that, something like polishing or deburring, or probably will get rid of that. Do you have any simulation software to predict all these things that we are talking, that irregularities coming and the force and energy required to do the forming and all? Do you use any simulation softwares?
Yeah, we do. We presently we use Simufact forming. I do not know which version. Yeah, but one of the latest versions. We calculate the flow of the material as well as the stress and the necessary forming forces later on for our machines also.
So according to you, if you see the carbon footprint for this process, how would it compare for equivalent process of, let us say, machining? Suppose you produce the drive shaft by machining versus this. In terms of energy required, how would they compare? One is, of course, lightweighting part, comparing the weight, but comparing the energy that goes into making the part. Do you have any rough estimate of what kind of carbon footprint saving we are having with these technologies?
You always have a smaller carbon footprint if you do not have to remove material. Let's make a comparison. We have two tubes.
Yes.
And the tubes usually are made out of sheet metal, welded tubes, welded precision tubes.
Yeah.
Drawn afterwards. With these tubes, we first do a turning operation, which means we take away material which we formed, where we took energy in, and we throw it away. With rotary swaging, your starting material is much smaller
Yes.
because you produce the length
Yes.
afterwards.
Yes.
And therefore you use much less material.
Okay.
You do not have material which goes into a recycling circle or something like this. So all these costs for recycling or so, you do not have it. So the electrical loads of the machine, they are nearly similar.
Okay.
So we have something like maximum 40 kilowatts for the very, very large ones.
Okay.
So Axial I'm talking here. So
Mm-hmm.
that is really comparable
Oh, yes.
with the
It is.
turning, grinding, and so
And
thing.
cycle time you just said is much smaller. So obviously the energy per part
Okay.
is going to be that much smaller.
Definitely. Typical cycle times here are really below half a minute. You cannot turn it. We also use turning here in our factories.
Yes.
As soon as we can, we change to forming,
Mhm.
especially if we have larger quantities. If you only have 4 or 5 pieces, of
Yes.
course you turn that. But if you
Yes.
have a production, then it simply does not pay off.
Okay, suppose in simulation you find out that certain energy is required for forming. Okay. Now you have choice of doing it slowly or doing it faster. Okay, energy remaining same. What are the challenges if you do it faster? If you reduce
Well,
cycle time too much, what will happen?
first of all, you're absolutely right because the flow curves is independent of the speed,
Yes.
how you change the volume or how you change the shape. You can make it faster, you can make it slower. It does not make a difference in energy. I would like to compare it with something
But
else.
in terms of
If you
quality, in
have,
terms of any other undesirable effects that
yeah,
if you do it faster.
let's come back to our 30 millimeter or so spline. If we
Yes.
want to form that,
Yes.
usually I have a splining speed of 20 millimeter per second, roughly,
Okay. Yeah.
which means that after 1.5 seconds, the spline is done.
Yes.
The rest, which sums up to 15 seconds, is handling time, the robot coming in and
Okay.
out,
Okay. Okay. Okay.
moving axles, and so, but the tool contact time is very low. If
Mm-hmm.
you want to make this faster or
Yes.
slower, it will not really it's not really a change.
Okay. In forming, there
The
is nothing
change
changing.
will
It's more in
come.
automation, I guess. It's more in the handling part.
Yeah, it's very automation.
It's not so much
Yeah, yeah,
the
yeah.
forming itself. Peter, there are some other competing technologies that do something similar to rotary swaging. For example, there is tube hydroforming, which can produce variable section of a tube from a tubular blank. How do you think it compares with the rotary swaging? Hydroforming is when you pump oil
Mm,
inside a tube and expand it
yeah.
to so that it fills the die.
I know it. There's an issue with hydroforming. Hydroforming usually is used for smaller quantities. I say, don't forget that they have a cost-intensive hydraulic system
Yes.
and they need to fill the complete part. Then they need to seal it. And when everything is sealed, it is perfect. So I really like it. However, until you seal it, you really have to work a lot. So it was some years ago. This was really interesting. However, we always had problems, or people who made this always had problems with the sealing and with the cycle time. Because you have to seal it, you have to close it, then you have to fill it, take the oil out, clean it, and so. And we saw that rotary swaging, for example, is much faster.
I'll tell my observations. I have two, three observations. First of all, hydroforming, you take a smaller blank and you enlarge it. Actually, you increase the cross section. Whereas in rotary swaging, most of the time you reduce the cross section. You have a bigger blank and you reduce the diameter of the tube. Okay, that is one
Mm.
difference. Other difference is, of course, in application. Hydroforming is more used in structural parts, substructure of a vehicle or engine cradle and things like that. I have not seen it being used for transmission parts. It is used for maybe manifolds and for pipes which are conducting fluid, for example. But not, I have not seen it being used for transmission parts, which rotary swaging is primarily meant for.
I think the wall thickness might be also a problem. We are working on metal walls or on wall thicknesses 5, 6 millimeters upwards.
Yes.
And this will be an issue for hydroforming. I have also seen hydroforming for motorcycle steerings, for
Yes.
example. When you see that this is 1 millimeter, 1.5 millimeter wall thickness, And this is easy to expand. If you expand something like 5-6 millimeters, you have to take care whether the material breaks, especially when you change the radius and when you change the diameters. That would be a thing. So what we see here is, I think it's a very interesting one, but it never was in the discussion for drivetrains or for shafts.
There is another technology which is a darling for defense products, rocket shells and things like that. That is flow forming, where you press the material between rollers and develop it on mandrel. You do extreme compaction so that your ordinary material becomes extraordinary in terms of properties and strength. If cold forming is same, and work hardening must be happening in rotary swaging, axial forming as well. So have you experienced any improvement in the material properties in terms of strength when you do these processes?
Definitely. This is what we call the cold work hardening effect.
Yes.
What we see when we work on the material, especially when we work cold, is that we get an increase in the tensile strength.
Yes.
Sometimes this is up to 20% of the tensile strength. I even have one case where we produced a special shaft with a spline on it, a longer spline on it, and actually it was foreseen to harden that spline.
Okay.
After we supplied the first parts, the customer declined hardening the spline because the cold work hardening effect was large.
Yeah.
Already hard enough.
Yes.
So, and with this, you save one complete step and an expensive step. So this is the effect of this cold work hardening effect, how we call that. And I think that rolling must be the same because it's also cold work hardening.
Yes. So do you target defense industry for your applications, for rotary swaging and axial forming? Yeah. Are you open to working for defense sector? As a technology, it can be an attractive proposition, I guess.
Oh, we did this in the years before, especially production of barrels, and so that was really a good business. But presently, this is a political decision.
Okay, that part apart. Talking as a pure technology, yes, it's a candidate for defense industry, I guess, as much as
definitely
is. My observation is that all these technologies have same problem, basically, whether we talk of composite, hydroforming, flow forming, rotary swaging, axial forming. And the problem is our designers don't know how to design a part that would use these technologies for manufacturing. Because many of these technologies will alter the properties of material. They may have some anisotropy, some crazy things. I mean, people are not used to designing hollow shafts, let us say. They don't teach it in engineering courses. They know how to design solid structures. They know how to design solid beams, how to design solid shafts, solid gears. But once it comes to making them hollow, the problem starts at design level. Because until we teach the designers how to design with those technologies, they will not design, and then downstream people cannot select these technologies because they can't change the process. They can't change the design. So that is something which is, I guess, holding up these technologies. Particularly in India, I am seeing that. I guess it must be same all over the world. So what do you say? What is your take on that?
First of all, it is definitely the same situation in Germany, because here in university, the people learn to turn, they learn to mill, everything like this.
Yes.
They're really good.
Yes.
But as you said, if it comes to texture, if it comes to calculating the work hardening effect, and really to work with this technology, I also saw that we work out some special classes to train engineers and teach exactly this. How can you design, for example, rotor shaft? How can you design this for cold work, for cold working technologies?
Yes.
I am not only thinking on the obstacles, what they have, I'm thinking on things like the real benefit, what they get out of that. Because what we usually do is we collaborate with manufacturers and then we receive the first print. Very often it's a laugh.
Yes.
And we start changing. And then it goes back and forth. Engineers tell us we need this and this. Okay, we can supply this and this. And at the end of the day, we have a real elegant one, like like the shaft I just showed you, which has this length here, hollow, very light, and extremely stable, so extremely hard. But this is only possible by training and by learning.
No, because
We
I
will
know
do
this
this.
case for additive manufacturing, for 3D printing, for example. See, you can 3D print a part that you are making by another process, but you get limited benefit of doing that. But if you
Yeah.
design the part to use the features of additive manufacturing to the hilt, then you get maximum benefit. The kind of money-wise benefit that you get are immense.
Yeah.
They are much more if you design the part, assuming that that technology is there.
And if you understand the technology, yeah, then you really will work with the texture. You will
Yes.
work with the hardening effects, and so
Yes.
and you will reduce your wall thicknesses. This is a learning process. You said it quite clearly, and we understand that. We will start this year with IMTMA with the first class of training. This will be something for engineers, mechanical engineers. And
Yes.
the idea is design of rotor shafts. So this is the first step. We will
Right.
see what we get from that. And
Yes.
from this on, we want to expand this so that we really can transfer this to young engineers, also other engineers, but not necessarily young engineers. But I would like to reach the younger generation just to see, look, there's something else despite turning and milling
Yes.
or drilling. You can work much more elegant. So this comes up this year. I hope we will have the first course by autumn,
Okay.
but I will soon speak with IMTMA.
Look forward to that. Sure, of course.
Yeah, let's see.
You have a lot of experience in selling this technology all over the world as well as in India now. How do you compare the response and market in India as compared to whatever reception you get all over the world for these technologies? So any observations on that? Anything you wish could have been different in India so that these technologies will grow faster? What's your take? What do you say?
From a technical point of view, it's the other way around. I wish some other countries would take this, what we do in India here. I really like that people are open for this new technology and that we start combining this technology. For example, at the moment, I have projects with with a large Indian company to add cold extrusion to rotary swaging. So to combine these two processes.
Mhm.
And this will be really something very, very interesting. People are curious, people want to do something new, and we have highly educated engineers and workers here. So,
Now, of course, Indian designers are working for all over the world. So
yeah,
we know we can
but
do a good
you
job
can
in
see it here.
kind of jobs. Yeah. So,
Yeah.
okay. Thanks, Peter. Thanks for a very nice informal chat. If there is anything, if there are any questions from the audience, which I'm sure there could be, we will get back to you for the answers, for the clarifications when they come. Until then, bye bye. Thanks a lot.
Thank you, Avinash. Have a nice day. Bye bye.
Dear audience, please be reminded, like the video, subscribe to our channel, give your comments as many as you can. Thanks. Good day. Bye bye. See you in the next video.